Bernard Becker Professor and founding director of the Institute for Informatics, Data Science, and Biostatistics, the I2BB, at WashU. He's also Associate Dean for Health Information and Data Science and Chief Data Scientist for WashU Medicine. Additionally, he serves as the chair of Washington University's Digital Transformation Initiative, including its accelerator, which just launched last year. Before joining WashU, Dr. Payne was a professor and chair of the Department of Biomedical Informatics at The Ohio State University. Before that, he earned an undergraduate degree at University of California, San Diego, and graduate degrees, including a PhD in biomedical informatics at Columbia University. We are really, really happy and excited to have you here today, Philip. I'll turn things over to you. Thank you.
Great. Thank you, Tom. And thanks for the really kind introduction and for the opportunity to join you all today. I am particularly excited as I feel like I have a unique opportunity to set perhaps the tone for some critical questions that hopefully this seminar series will help you to answer. And of course, I'm always happy to interact with my friends and colleagues in New York, which has a special place for me since I spent a lot of my early career just a little bit uptown from all of you. So with that, I want to sort of set the stage for today's talk. I included this quote from Fei-Fei Li at Stanford, which I think really is emblematic of the current state of AI, in that despite what I would label as perhaps almost breathless abandon about the potential of new and emerging AI technologies, we are still presently just looking at what I think is the tip of the iceberg in terms of what is possible by bringing these technologies into the research and clinical environment. So with that as sort of a starting point, I think we could all agree that it's almost impossible to open a journal or to look at the lay press or to turn on the television or surf the internet or any other source of information and not find yourself reading or thinking about the role of artificial intelligence in shaping almost every aspect of our society. It was actually somewhat comical. This past week, I was at the American College of Medical Informatics Winter Symposium, and we congratulated ourselves when we went almost 4 hours without mentioning AI during a conversation. That's an achievement for us. So I think, the reason why I started with this is that, this is a topic that is front of mind for a lot of individuals who either interact with the research and clinical care environment, or are working within those environments, or are driving innovation that will improve, again, how we conduct research or deliver care. What is interesting, and I think an important observation, is that the use of AI in health and healthcare is not new. In fact, the origins of the field of biomedical informatics as a scientific discipline date back to the late 1950s and early 1960s, when the very first reported instances of the use of AI to drive clinical decision-making were published on. So this is not a new phenomenon. What I think is different today is that these technically are more plausible technologies than they ever have been before. So it's not that we are looking at a new concept, the use of AI, but rather we're looking at an important inflection point where these technologies have become reasonable to deploy, not just for experimental purposes, but for real-world purposes. And we know that this is dominating the landscape of not only research and sort of the economy, but also just healthcare delivery. So this is an infographic from our friends at Gartner that talks about sort of the current state of deployment of AI solutions that can be used to inform, support, or enable the delivery of clinical care. And it is sort of oriented around sort of the number of respondents that have reported across major academic and integrated delivery systems the use of AI, and how important they see these technologies as being in terms of driving care transformation. I would point out that despite a lot of the enthusiasm around recent generative AI technologies like ambient AI for clinical documentation, many of the most important and most advanced deployments are actually around sort of relatively unglamorous parts of healthcare, automating sort of workflows and other activities that are largely administrative or logistical in nature. And I think that's actually an important observation, because these are the places where we can take friction out of the system and enable care providers to be able to focus on their patients and perhaps improve shared decision making by taking the computer out of the middle of those dynamics. Now, for those of you that aren't sort of AI people or didn't sort of grow up thinking about how we apply AI in healthcare, this is the ultimate cheat sheet for how almost all artificial intelligence works in healthcare. And if you take nothing out of this diagram, it's that while these are sophisticated technologies in terms of how they're implemented, the fundamentals are relatively simple. And they really are based on this idea that humans, if you sort of study the cognitive psychology of how we navigate the information world around us, we rely upon pattern recognition, right? So, for example, if you walk into a room and you see a table in front of you, you don't have an encyclopedic knowledge in your head of what every table in the world looks like. What you have is a pattern that you have learned through experience that tells you that a table may have a top and legs, and if you set something on it, it's unlikely to fall on the floor. What computers do when we build artificially intelligent systems is simply replicate that type of pattern recognition just faster and with a greater scope or scale than our human brains are capable of. And so that means the basics of building artificial intelligence systems, whether they are for analytical or generative purposes like ChatGPT, involve collecting some sort of data that can be used to ascertain those patterns, training the model, which is really finding those patterns and encoding them in a way that the computer can understand them, and then deploying that pattern recognition based on that learning process in the real world, studying how it performs, and then ideally monitoring and optimizing and repeating that process. And one of the other important things about this sort of diagram is that this is a dynamic process. When we develop an artificial intelligence tool, it is not fixed in time and space. We build it, we deploy it, and it impacts the environment in which it's used, which in turn impacts its performance and requires constant monitoring and optimization. This is also why some of the issues that we face around regulation, the development of evidence standards, and other dynamics around the safe and rigorous deployment of AI are very challenging. These are not like small molecules, novel diagnostics, because they constantly change. They are dynamic systems. Now, as I've already alluded to, there's certainly a hype cycle around these technologies, and it is dominating not only healthcare, but lots of other parts of our economy. So again, this is actually the sort of well-known Gartner hype cycle that talks about sort of this idea that when new technologies first emerge, there tends to be very inflated expectations of what they can do. And then oftentimes when they fail to deliver, people become concerned or disillusioned, and really achieving some value from novel technologies requires sort of the discipline and the injection of time and resources to navigate that trough of disillusionment and actually get to productivity, which is downrange. I would draw your attention to the fact, and by the way, as much as I hate to rely on Gartner material, I would point out that they are generally right when they produce these hype cycle charts. And there's innumerable examples of them correctly predicting sort of the navigation of a technology through this hype cycle. And I would point out that generative AI is at the peak of that sort of height of inflated expectations. So I think it is reasonable to anticipate that as excited as we are about ChatGPT and other generative AI technologies as the newest addition to our AI toolbox, the reality of how they're going to be used is probably going to look a lot different than what we're reading and thinking and talking about today. Now, as I mentioned, generative AI is perhaps one of the most popular areas that we talk about in sort of the present time around the use of AI, especially in healthcare. And there are many well-recognized large language models, which are examples of generative AI. I would assume that many people on this call have used OpenAI. There are other competing models that are very similar, such as Google's Gemini, as well as a number of models that Meta has produced. But the basic idea here is that instead of having models that predict a decision, these are models that actually produce new content. And that's why they are called generative AI. So the basic idea then is that they analyze large corpora of domain knowledge, usually in textual or equivalent form. That's why we call them large language models. They, again, find those patterns, which are often patterns of how different tokens of knowledge, words, for example, transition from one to another in written or spoken language, and then use that model to predict how one would respond to a prompt, right? That prompt may be, tell me what is the current set of problems that this patient is being admitted for. And a large language model would be able to look at the content that is in the EHR and predict which sequence of words would be put together to create a plain English description of those discrete data that exist within the EHR. Now, right now, when you use these tools, and there's some results already, I would point out that almost all of them are just trained on general knowledge extracted from the public internet. We have yet to see what these models look like or how they perform when they've been trained using domain-specific language, such as what we might find in the domain literature of medicine or in the EHR. So one of the things I often say to people is, they may be surprised that if we use a large language model to extract knowledge from the clinical chart and we decide that it's 80% accurate, that it's not a whole lot better than, say, statistical natural language processing tools that we have used in the past. Except that it has likely achieved that 80% with no tuning, no optimization, and it has done it based on just general knowledge from the internet. So one could imagine in the future that that performance is going to continue to get better, and there's already evidence in the domain literature and a number of research projects that would point to that outcome. So that drives to sort of the mini hype cycle model that I'm showing here around sort of generative AI in healthcare, and really this idea of how we move from the hype to sort of impact. So you can see here that there are some interesting aspects to this that go beyond what you often hear about. So, people are really interested right now in how we would integrate these technologies with electronic health records to automate things like chart summarization or clinical documentation. Our organization is doing that right now. We have 100 primary care physicians that are using a Microsoft and nuance-based generative AI tool to produce documentation during primary care encounters and basically do that in real time as a means of allowing the physicians to focus more on their discussion with the patients and shared decision-making as opposed to documentation at the keyboard. We'll find out in 8 to 12 weeks how high of quality that documentation is and the acceptability of the technology to both our providers and patients. And I would guess you probably have similar studies underway right now in your system. That is still very formative. We don't really know if that's the ultimate use case where we're going to get substantial value and impact. I would point out, if you look at this diagram, and something that's a little less well understood are consumer-oriented large language models. For example, tools that might help our patients to find information on our websites through the use of chatbots or the equivalent, or perhaps for after-visit summaries that are more readily interpretable by patients. These are less glamorous applications of large language models, but perhaps areas where we will see greater value early on, because again, they will take friction out of the system in terms of people's information-seeking behavior. And there is a tremendous amount of activity in academic medicine around what I'm describing here. I just highlighted a few recent articles from Becker's, as well as a number of newspapers, talking about how academic health centers are really doubling down on building the infrastructure, the teams, the governance, and the processes to take these types of technologies out of the lab or out of sort of the hyper-scaling large technology firms and put them into the clinic. Clearly, there is a desire to find out how these technologies are going to change, again, health and healthcare. And there's a really interesting report, if you are curious about this, from the National Bureau of Economic Research. Luckily, one of my colleagues in our business school pointed to this report, because I don't know that I would ever read something from the National Bureau of Economic Research. But it is a fascinating report that describes all of the different use cases for both analytical and generative AI in the healthcare setting, and the types of sort of impact that these technologies may have, how mature the technologies are, and whether or not they have direct or indirect returns of investment. This is a really interesting, almost secret decoder ring to think about, okay, what are the problems that I think we should be tackling in my healthcare delivery system? What are the technologies that are available? How mature are they? And how much risk or cost am I willing to take on in order to adopt and evaluate these technologies? So if you've not seen this report, it's a very interesting sort of comprehensive view of the current state of the art. And I really recommend, actually, if you take a look at it, both focuses on the inpatient space as well as ambulatory care as well. But one of the things I want to sort of end this first part of the talk focusing on is that it's really essential to understand that AI is not a replacement for humans in healthcare. And that's something that people are very concerned about, I would argue rightfully. However, if you look at sort of how we are using these technologies and where they have their greatest impact and benefit, It's not AI acting alone. It's actually AI acting in tandem with humans. Humans are extremely good from a cognitive standpoint in recognizing patterns, as I alluded to earlier, in incomplete or otherwise difficult to interpret data, which computers are not. In turn, artificial intelligence is really good at filtering important signals out of noisy data and allowing us to get to the more critical data more quickly. That's why humans and computers working together are superior to either working alone. And so this diagram is actually extracted from a paper written by my colleague Chuck Friedman, now at the University of Michigan, where he postulated a fundamental theorem for informatics, which is that informatics is a science that is really anchored on a concept that humans and computers working together are better than humans or computers working alone. I'd also point out this sort of connects to a number of important concerns that we should be thinking through when we use AI, especially in the health and healthcare domain, such as the potential for bias that can be encoded into these algorithms, the limited nature of the data and knowledge bases we have to train them, back to my sort of cheat sheet that I showed you before, and frankly, an understanding that by and large, even though we think of these systems as being very smart, and they can appear to be very smart, they actually aren't by any sort of quantifiable measure of intelligence. In fact, the voice assistants that you may be used to using at home, right, which seem quite intelligent, they can tell you the weather, they can order you groceries, they can answer your questions, etc., appear to be quite intelligent. They actually have the innate sort of intelligence of roughly a 4 to 5-year-old. They appear smart because they respond much more quickly and at a scope or scale greater than what the human brain is capable of. And many of you may be aware of this, but like the fundamental metric that you can use to sort of understand why this sort of human computer dyad is so important is that the human brain is optimized to recall and reason upon 7 plus or minus 1 to 2 pieces of information at any point in time. That's actually why phone numbers are the length that they are, because they're a number that human beings can remember. So think about the amount of data that we produce in the healthcare environment. It's not surprising that humans cannot reason on all that data at one time, even though we have these great pattern matching skills. And that's where the computer becomes very important with that scale and speed in terms of filtering and allowing us to get to the right data more quickly, where we can use those human cognitive strengths. So that leads to the second part of this talk, which is framing this opportunity around the use of artificial intelligence as a sort of fundamental part of building learning health systems. And since this is a CTSA-oriented audience, I don't think I have to spend a lot of time convincing you that there's been a lot of discussion and a lot written about building learning health systems. And there are a variety of definitions that have been proposed for what constitutes a learning health system. You actually can see here quoted one such definition from a seminal report that was written by the National Academy of Medicine. But the fundamentals here are pretty straightforward, right? In a learning health system, we would learn from every patient encounter, and then we would use that learning to improve the care that we deliver to that patient or to their family or to their community members. And ideally, that creates a more virtuous cycle whereby it's not sort of unidirectional, sort of research is translated into practice. Actually, we are constantly linking across scales of measurement and learning and sort of repeating that learning cycle in as near real time as possible. The one thing I will say, though, about the learning health system, and this is my one sort of editorial comment on this slide, is that many people think of it as almost a physical thing, right? If I build a space or I have an electronic health record or I have the right data analytic platforms, I will have a learning health system. I don't believe that's the case. I actually believe that a learning health system, more than anything, is a set of behaviors. Because if we encode those behaviors where we think about clinical care as an opportunity to learn, and then we think about research as an opportunity to create rapid feedback cycles to clinical care, and we no longer think of that sort of translational spectrum as unidirectional, we are moving towards a set of behaviors and frankly incentives that make the learning health system work. And so really, again, I'll reiterate that the learning health system is the vehicle whereby we can improve quality, safety, outcomes, and value of care by using all the tools and mechanisms that are often familiar with as basic clinical or translational researchers, but simply embedding them in the care delivery environment and shortening that cycle time. So we know how to do these things, but perhaps the resources and incentives today aren't always aligned to make that as readily available as we might like. And so this is my sort of version of thinking about how we operationalize the learning health system, and it's certainly an informatics-centric view. But the idea here is that whether it be research or healthcare operations, we are constantly building data. I kind of think of this as almost a data exhaust, right, that sort of is produced from all aspects of our work. This creates this afferent process whereby we can generate information, right? So we wrap that data in context and we make sure that we understand where, when, and how it should be delivered. That's ultimately how we produce knowledge that is actionable. And then we, again, put that knowledge back into the care delivery environment. That could be decision support, it could be analytical tools, it could be new educational curricula. Who knows? It could be a new technology that we haven't even envisioned today. And then we constantly evaluate and optimize. And think about that. That's a really close parallel to what I introduced earlier in terms of that cycle for building artificial intelligence. And ultimately, we try to measure impact, and that's the efferent process, and that leads back to clinical care, and then we repeat. And as you can see, I've sort of embedded this concept that AI is perhaps one of the most important enablers of building this, because this is, again, a set of processes and behaviors that produce tremendous amounts of data. We want to find the meaningful patterns in those data. We know that humans and computers working together are better than either alone in finding those patterns, but we must have better tools in order to filter, sort, and understand where the important signals are and all of that multi-scale data. And that's where AI becomes the most important enabler. And so if you put all of these messages together, what do you arrive at? You arrive at this idea that artificial intelligence really is the sort of vehicle whereby we digitally transform healthcare to build that learning health system. And if you're not familiar with this phrase, digital transformation, this is really just the idea that we take a digital first approach to everything we do. All things being equal, if we have available data, communication, or computing technologies that can make a process or environment better, we should attempt to do so. And so if you think about that in healthcare, it's about taking the next step beyond the adoption of electronic health records or other computational systems and truly using all of that data and communication and connectivity technologies in order to improve important outcomes like, again, quality, cost, outcomes, and value. So that leads to really 4 really important questions that we should all ask every time we are setting out to implement some part of a learning health system using AI. And those 4 questions are right here on the slide. First and foremost, if we're going to do this, is the task that we are trying to address even the right kind of task to build the learning health system? And if the task is appropriate, do we have the data to support it? And if we do have that data, do we know the evidence standard so we can assess whether or not we've been successful? And then if we overcome those 3 important potential barriers or opportunities, do we know how to bring this back into the real world? And I often tell people, you can have the best algorithm in the world, but if people can't use it, it will still fail, right? So an elegant computational solution without sort of addressing human factors and real world workflow will absolutely fail to deliver results. And so every time we undertake a project where we're seeking, again, to build this digitally transformed AI-enabled learning health system, we have to be able to answer these 4 questions. So let's unpack that a little bit more. So I said the first question is the task the right kind of task for us to tackle in this type of environment? So this is my one, a little bit sort of in the weeds informatics slide, but just bear with me. One of the fundamental sort of aspects of informatics as a scientific discipline is that we as investigators often think about how do we take data, apply the appropriate context to it such that it becomes information, and then, as you might have heard me say just a few slides ago, deliver it in the right time, place, and format so that it becomes actionable knowledge. And there's a vast body of theory and methods that allow us to do that, right? Because there are fundamental types of knowledge that we as humans reason upon, conceptual, strategic, and procedural knowledge, which are defined here, and I won't go into sort of a lot of detail around, but these are distinct and complementary knowledge types that cognitive psychologists have literally studied for decades. And in informatics, we attempt to translate those knowledge types into symbolic representations that computers can reason on so that they can replicate or support human decision-making, back to that fundamental theorem that I showed before. An example I gave here is that, for example, if I just told you the number 250, and I didn't tell you that it was a glucose measurement or the units, that number 250 by itself is basically useless. But once I give you that metadata, I wrap that 250 in context, and I tell you that, like I said, it's a glucose measurement, and here are the units, and perhaps I tell you what the normal range is. All of a sudden, you can say, oh, okay, this is an abnormal finding, and it's something that we may actually need to do something with clinically. And then importantly, I might actually have to deliver a report or a decision support alert or something else to a clinician to say, hey, your patient has an elevated blood glucose level. You may want to access this available evidence to look at potential treatment protocols because they may have type 2 diabetes, for example. So that's that whole sort of data information knowledge life cycle. So why am I sharing that with you? Well, the reality is that if we are going to build a computational tool to support a learning health system, we need to actually make sure that we can complete that full data information knowledge life cycle. And we can ask questions as to whether or not a task is suitable for that type of life cycle by using the data we actually have in our electronic health record or in our laboratories or both. So this is an example of a study just like that from our team here at WashU. And this was actually looking in our electronic health record to identify previously unknown opioid drug interactions that occur in inpatient settings. So the basic premise of this study was, okay, for patients receiving opioids in the hospital, how many had adverse drug events? And if those adverse drug events were associated with another drug that they were prescribed while they were in the hospital, were these drugs that we knew from the canonical knowledge, likely from the FDA package inserts or other published documentation, were associated with the use of that opioid, or were they novel? And you can actually see from sort of the sort of scatter plots shown here that there actually are a number of drug-drug interactions that are associated with potentially highly deleterious outcomes like cardiorespiratory arrest or a PE, renal failure, or pneumonia that are not reported. Those are the red dots in these sort of scatter plots in the available literature. So why am I showing you this? Because this is actually taking our raw data, putting some context around it, what other drugs did the patient receive and what outcomes occurred, and then visualizing it in a way that we can say, yes, there are previously unknown drug-drug interactions involving these opioids, and we have data to support in our own electronic health record with our 7.5 million patients that are there in our data warehouse, that these events are occurring with enough sort of frequency that we should explore them further. So this is an example of a task that's well suited to the use of artificial intelligence because there is the ability to go from data to information and knowledge. And you don't just have to take my word for it because we can empirically show it with studies like this one. So then we go to the next question. If I've now established from a sort of empirical perspective that the task is suitable to be able to complete that data information knowledge life cycle, I still have to make sure that there's enough of that data and I understand it well enough that I can actually design the project appropriately. So this is one of my examples that I often use when I'm teaching and in lectures like this, where I try to explain like why using EHR data is so difficult. So let's say I want to ask, back to my prior example, this really simple question. Did we give a patient an opioid? The bad news is, despite the billions and billions of dollars that we have spent on installing electronic health records, there is no direct measurement of whether or not the patient received a drug. There's lots of surrogates. There may be order entry data that tells us about the intent to give that drug to a patient. There could be pharmacy data that tells us whether or not the drug was available for administration. There might be an administration record that says somebody believes they administered the drug to the patient, or maybe there's bedside barcode scanning or some equivalent medication reconciliation. And I have to make a decision every time I query EHR data. Am I going to use one of these? Or am I going to use a combination of these to create sort of a synthetic variable that becomes my ground truth? And that's just for asking the simple question, did a patient get a medication? Now, the other challenge with this is that if I use a different set of these features than my colleagues do, we may get different numerators and denominators for the basic rate of drug administration because these data are not always synchronous with one another. So this is a simple question. And the reason why I bring this up is that when we are using EHR data, which is a powerful source of data for research, and I hope you hear that part of my argument. I believe we should use every piece of data that's in the EHR, and I believe that's our living laboratory for building these types of learning health systems. But I also believe we have to enter into this with a sort of realistic expectation around the challenges that we may encounter. And you see a whole bunch of them that are sort of enumerated here. I won't read them all, but this is from a paper that a large group of individuals wrote together as part of the AHRQ funded electronic data methods forum actually quite some time ago. And it's one of those papers that sort of stood the test of time because these fundamental challenges were identified in 2013 have not changed today, which are really all the caveats that you see listed on this slide. So let's go back to another data-driven example, what that might look like if we were to sort of look at this from a research lens. So this is a study where we looked at the ability to use mortality risk prediction scores to anticipate patient deterioration for those individuals either with sepsis or at risk of sepsis in an inpatient setting. And you probably have all heard of many of these different mortality risk prediction tools, right? Apache, SOFA, Muse, News, SOFA, all very well validated mortality risk prediction tools, some with very good performance measures in the published literature. But there is one intrinsic flaw to all of these measures. They have largely been built using administrative and claims data that does not exist when the patient is in the hospital. So if I want to use one of these in order to ascertain whether or not a patient is at risk of mortality and therefore make a decision to perhaps mitigate or manage that risk, I can't actually use these. In fact, this study, which is cited here, we took all of the sort of major mortality risk prediction metrics that you've seen here, and we simply attempted to calculate them using the data that was in the EHR that was computable and available during a clinical encounter. And then we compared the performance of those measures for mortality risk prediction as compared to what was published in the literature. And here's the bad news. They were all uniformly bad. None of them were effective in predicting mortality. So this is actually a good example of a situation where perhaps we might have a problem that's suitable, right? Predicting mortality and anticipating how we should intervene, but the data is not suitable, at least using the measures that we have at hand. And that would argue either we need to change how we collect data, or we need better measures for risk prediction, or both. This is another example, and it goes back to my sort of caveats around the use of EHR data. You might say, okay, Philip, so one institution in that prior study couldn't replicate sort of all of these different mortality risk prediction algorithms. But what if you combine data from multiple institutions, right? Data sharing will give us bigger, better data sets, and therefore we'll be able to overcome these challenges. So this is a paper where we actually looked at a relatively simple problem, which was, could we use coded data from the EHR to find patients who have type 2 diabetes? Now, I think many of us know that you have a lot of patients probably in your hospital right now who are type 2 diabetics, who are receiving drugs for their type 2 diabetes, and their problem list will not say that they have type 2 diabetes because that's not what they were admitted for. So we often have to triangulate, back to the example I gave you, who type 2 diabetics based on lab data, medication data, other concomitant diagnoses, and produce that synthetic variable that says, oh, these are type 2 diabetics. Might be easier if we documented what problems people actually had when they came to the hospital, but in the absence of that, this is our next best opportunity. And these two Venn diagrams show two different large academic health systems that are multi-hospital with the overlap of codes that we would expect to be useful for a standard phenotyping algorithm to identify type 2 diabetes. And what you should take away from that is that the magnitudes of those overlaps are vastly different between these two hospitals. And that is a function of local workflow patterns, the population dynamics, as well as the preferences of the individual providers and how they've configured their EHR, amongst a variety of other factors. So what this tells us is even if I want to combine data across multiple sites, I'm going to have to be very thoughtful about how I phenotype my patients to decide whether or not they have the condition I'm interested in, because in fact, the data is highly variable even when it's codified. So I gave you a positive example in the first case. Yes, we can find a task that's suitable to using our data, in that case with opioids. And then I gave you two negative examples where perhaps even if we have a good task, the data is not suitable to support that type of analysis. Now, I gave you negative examples. There are plenty of positive examples. And so then we could move on to the next question, which is, what's the evidence standard? How do we decide whether or not we know that some digital intervention, for example, an AI intervention, is actually working? So, especially with an audience associated, again, with the CTSA, I don't think I have to spend a lot of time convincing you all that one of the gold standard study designs that we use in clinical research is the RCT, right? And the most basic version of the RCT is pretty straightforward. We are interested in some phenomena. We randomly put people into intervention and control groups. Some people get the intervention, some people don't. And ideally, if they're appropriately demographically matched or otherwise randomized, and we manage any sources of bias in that process, we can compare results and say whether or not the intervention performed better than the absence of the intervention, or say a standard of care. And there are a lot of reasons why the RCT is a good benchmark study design, and certainly there's lots of derivatives and more advanced study designs, but the fundamentals of randomization and management of bias in order to reduce internal and external sources of concern around validity are pretty tried and true. However, now let's imagine I'm using artificial intelligence and I'm going to predict individual patient trajectory, right? So not for the average patient, but for the individual patient in front of me. What's going to happen? I'll use my sepsis example to this patient in the next 8, 12, or 24 hours. Well, if I was worried about something that was high prevalence, let's say it was my type 2 diabetics, and a population, there's a relatively high incidence of that disease. If I randomize people into intervention and control groups, there's a pretty good chance, even with random selection, I'm going to get two balanced groups, and therefore I can compare the results. But if I'm performing an N of 1 or an N of 2 study, which is often the case with these highly tailored digital interventions, randomization is highly likely to give me a very imbalanced group. And this is a problem, which means I can't really compare between these two groups. And therefore, it's sort of the fundamental basis why the RCT is a good study design in many cases starts to be less apparent. However, all is not lost. We can now perform pragmatic trials that are actually dynamically balanced using electronic health record data without having to recruit patients prospectively. So this is an example actually of a project looking at sort of the prediction of Alzheimer's disease related dementia using a variety of different modalities, including features extracted from neuroimaging, cognitive assessments that are directly conducted with patients, genetic testing, lab data, demographics, and clinical notes. And actually, in this first study, what we did was actually just look at the relative availability and use of those data and a variety of predictive algorithms, and then actually combined those data sets derived from our electronic health record and from the Knight Alzheimer's Disease Research Center here at WashU to basically run a series of pragmatic trials to understand whether or not we could or could not adequately predict risk of accelerated AD dementia in a 24 to 48 month time period after any given cognitive and clinical assessment. And the takeaway is actually you can do that and you can differentiate patients into those groups. And this was done with a dynamically balanced study design that was run on pragmatic data extracted from the EHR. Same thing in a different disease state, in this case, a rare genetic disease, neurofibromatosis type 1, where we're actually able to show that through, again, this dynamic sort of pragmatic study design, combined with sort of what I would describe as sort of a EHR data enrichment paradigm in which we took EHR data and enriched it with additional detailed demographics as well as clinical features that were extracted by domain experts in a registry study, we could actually produce a predictive model that would give us a high degree of accuracy in terms of anticipating which patients with NF1 would develop a number of deleterious subphenotypes like optic pathway gliomas, ADHD, or plexiform neurofibromas, which are painful nerve sheath tumors. This is interesting because in this disease, we're very good at diagnosing NF1, but we're very bad at anticipating which one of these outcomes the patients may have. And therefore, we subject all of the children with NF1 to very aggressive monitoring, imaging, and other clinical management paradigms, which may not be necessary because there's a large number of patients that will simply have a relatively indolent form of the disease, whereas others will have a very aggressive disease that will result in some of these outcomes. So doing this dynamically sort of organized and pragmatic trial using data in the EHR and complementary data sets actually allowed us to use AI to predict outcomes for these patients and therefore stratify them into risk groups that could be used in real time to guide clinical care for them. Okay, so far our questions were, is the task right? Do we have the data? And do we know what the evidence standard is in order to be able to assess success? So let's say we've addressed all those questions. We still need to get that intervention back in the right time, place, and format, back to this sort of idea that I introduced earlier to make sure that people can use it in the real world. And so I gave you earlier sort of my sort of editorial comments about the Gartner hype cycle. Now I'm going to give you a different version of that, which is what's called the intermediate effect. And this is something that's been studied well in the cognitive psychology literature, in that anytime we introduce a new digital intervention into, for example, clinical decision making, we often see a decrease in performance, let's say accuracy or speed of decision making, before things get better. Anybody who's used a new electronic health record has experienced this trough of despair that you see at the bottom. Because what happens is that we introduce the technology and it fundamentally reorganizes the data, information, and knowledge that we as humans need to interpret to apply that expert pattern recognition that I talked about earlier. And so during that time, we become less performant, less efficient, because we basically have to rewire those patterns in our brain. And what's important is actually not to sort of give up when we get to this trough of despair, but rather to inject additional training, support, and other tools to help people move through that trough and then ideally achieve some new performance level that will be better than where we started. But I will tell you right now, if you look at the playbook for 99% of digital health interventions, EHRs, clinical decision support, lab systems, I could just name like 100 systems now. We ignore this every single time. We turn on the system and we basically say good. I often liken it to if you were teaching someone to drive and you said to a person who had never seen a car on the road, here's a car, I'm handing you the keys, here's the steering wheel and pedals and some buttons, good luck. That's how we introduce technology into the healthcare environment today. So what if we didn't do that? What if we actually studied what was necessary for humans to be able to adapt and use these new technologies? So this is one example where we're using neural networks to predict, again, the sort of likelihood of a number of deleterious outcomes for patients in the ICU. And, you know, neural networks, while very performant in terms of predicting outcomes, are very hard to deploy clinically because they're a black box. So there's not really a great way to know how the neural network performs. And therefore, if we want to explain it or render it plausible to our clinician and users, it's extremely difficult to do. So this is a relatively simple intervention. We simply used our model applied to a simulated group of patients. We took a demographically matched group of real patients. We plotted those same criteria, and then we showed the two curves next to each other. And we presented this to the clinicians that would use the predictive algorithm. So basically here, what we're just showing you is that the relative distribution of what the computer predicts and what happens in the real world with a matched population is the same. It turns out, if you put this in front of clinician scientists, this is a very compelling argument that the neural network is performing in a way that is expected and is biologically and clinically plausible. There's no magic here. This is literally using a self-explaining neural network and basic data visualization to be able to give a human end user a view of how the model is performing that's accessible and understandable in the clinical context in which the model is meant to be used. And by the way, this doesn't just stop with predicting what happens to patients. You can actually do this with clinicians as well. So we have a very large program now where we actually apply predictive modeling to the log files from our electronic health record. And we can actually anticipate, based on how people interact with the electronic health record, whether or not they're experiencing burnout and are more likely to actually produce a medical error as a function of burnout than those that are not. So I will spare you all the excruciating details, but we started with a study with a lot of surveys and sensors where we actually looked at physiologic and actually self-reported signs of burnout in our providers. We then looked at how they interacted with the electronic health record. We found that there were substantial differences in how they navigated the EHR in terms of speed and accuracy of task completion. And we actually found patterns that were reproducible. And then we can actually use that in the EHR to sort of a priori identify those individuals that may be suffering from burnout without self-reporting it, and perhaps give them a behavioral economic nudge to say, before you order this test or before you order this medication, perhaps you may want to double check that decision because it appears that you are sort of in a position where you might be making an error. So this is actually giving people the ability to self-police in an environment where burnout is extremely common. And this is a way to optimize the EHR experience in a way that responds to the human's needs in that clinical care environment. So just to sort of round things out, I do want to sort of step back from those technical questions and just take a moment and talk about sort of a broader socio-technical context for a lot of the areas that I've just touched on. And in particular, I want to just introduce you briefly to some work that's taking place at the National Academy of Medicine, as well as through the Coalition for Health AI, or CHAI. So, one of the challenges with all the work that is described to is that we are going to have to deal with some very complex ethical, legal, and social implications of these technologies. There is a desire by many government agencies to regulate these technologies, which has both pros and cons. Not to mention, there is a great mismatch between the speed with which these technologies are being produced by hyperscaling technology firms and startups alike, and then our ability in healthcare provider organizations or academic medicine to sort of adopt and evaluate them. So one of the things that we've been doing through the National Academy of Medicine is establishing what is now called the Healthcare Artificial Intelligence Code of Conduct. And the idea here is to have a set of shared principles and guide rails that allow people to be able to ask and answer the right questions in this socio-technical context when they are designing, delivering, and evaluating these types of clinical AI solutions. And you can see them sort of enumerated here. They're not particularly surprising, but they are important to sort of codify. Things like we want to make sure that our first and most important aim is advancing human health. One need not look too far in the literature to see lots of concerns about the use of AI, for example, in the determination of prior authorizations for care delivery to see sort of a potentially alternative use of these technologies. We want to make sure that these technologies are equitable and those benefits accrue to all patients and communities. And frankly, that the people who are subject to decisions made through AI are partners in that process, right? This is sort of the idea of disclosure and transparency around when and AI is being used. Not to mention, this is an opportunity to restore sort of the ethical compact between providers and patients by making computers a less sort of visible impediment in that interaction, and then making sure that we're constantly evaluating and understanding the impact of AI, and then working together as a community across government, industry, care providers, payers, patients, and many other stakeholders to make sure that we're constantly learning. And so I would encourage you all, there's a lot of work underway here. There's a number of meetings, as well as sort of working groups focused on almost all domains of medicine. Take a look, there's a URL, which is super long at the bottom of this slide, but don't worry, I'm gonna give you a link to my slides at the end, so you don't need to commit it to memory right now. And here again, I'll just sort of introduce this here, and you can take a look in more detail either on the website or in my slides. But these are sort of the specific principles that come from sort of those guiding concepts that I just showed you a moment ago. And I think, again, while many of us in this environment may look at these as painfully obvious, again, achieving shared understanding and agreement that these are the principles that we're going to hold everyone in this broader health and life sciences community accountable to is going to be essential to achieving some appropriate pathway to navigate all those complex ethical, legal, and social issues. I'd also point out that there is a similar and partnered group that has emerged from another major health systems, which is the Coalition for Health AI, if you're not only familiar, or CHAI. And this is a group that is doing similar work, including creating the idea of creating basically benchmarking laboratories that will be used. Think of it like an underwriter's laboratory, if you would, but for AI solutions that can be used in health and healthcare. And I think this is very important. If you think about it, if organizations like ours, Washington University or Weill Cornell, struggle with some of the complexity of implementing these technologies, what does that look like if you're a small community hospital or a sort of practice with one or two primary care providers in the community? The reality is this is very hard, and there need to be standards and tools to help everybody equitably and appropriately adapt these tools. And that is something that CHAI is looking at as well. So if you're interested in that, I highly recommend you take a look, and they have a number of convening events that you can get engaged in. So let me just sort of wrap up so we have some time for questions here. And I'm going to say sort of, if I sort of come back to this idea of the intersection of AI and the learning health system, the brief summary would be lots of promise, but lots of open questions. We have to learn from other fields, and I'll talk about that in just a moment. And I'm going to sort of make a final plea to all of you that we need to rethink the sort of differentiation of basic and applied research in order to achieve these goals. So this is my sort of summary statement. If you didn't pay attention to any other slide, this is probably the only one you should pay attention to, which is basically that there's a lot of promise if we can figure out how to bridge AI and learning health system concepts in terms of improving quality, safety, outcomes, and value of care, and ultimately the health of populations. So I think back to that quote I started with from Fei-Fei Li, this is a huge opportunity space for us. But inconsistent data quality, challenges around picking our evidence standards, not to mention sort of the lack of clarity around how and where to integrate these tools at the point of care and beyond, those are significant threats. And if we don't do the hard research and study in order to address those open questions, we will probably not achieve that benefit that I just talked about a moment ago. And so whether or not the learning health system paradigm coupled with AI will achieve that sort of grand vision that's been argued by many thought leaders in our field, I think is unanswered. I think if we can answer these questions that I've just illuminated here, perhaps we will be able to be more certain about that. But I would argue still a widely sort of to be determined concept. And therefore, there's a lot of difficult and rigorous work for us to overcome that high and actually do the sort of science that we are all trained to do in order to, again, ask and answer those 4 critical questions that I introduced. I will say, this would be a whole different lecture, but I encourage you all, if you get a piece of homework out of this and you want to go deeper on this topic, that one of the reasons why this is so challenging and why there are so many open questions is that healthcare and learning health systems in particular are what is often referred to in the engineering literature as an ultra large scale system. And ultra large scale systems exist in other areas like air traffic control or energy infrastructure. They are intrinsically complex. They fail frequently. They have very diverse end user needs. And we actually have to design for that complexity. And I would argue that very little of the knowledge that has been developed in these other fields that is relevant to building high performance learning and resilient systems, for example, again, in air traffic control or in energy infrastructure, have not been brought to healthcare yet. So if we're going to build this AI-enabled learning health system, I would suggest that we beyond the health and life sciences and learn from our engineering colleagues in equal measure in order to achieve these goals. And then lastly, I gave you a sneak preview of this. I also think that we as scientists and leaders have to consider what is the real dichotomy that exists between basic and applied research when we're trying to pursue this work. Traditionally, science has been oriented around this somewhat unidirectional sort of translational concept from basic to applied or clinical research. However, if you read this book, which I actually really enjoyed by Donald Stokes, called Pasteur's Quadrant, it makes an argument based on some of the work of Louis Pasteur that use-inspired basic research, where individuals rapidly cycle between basic and applied research, and their basic research is informed and driven by those applied problems, and vice versa. The applied problems are solved using basic science solutions that those individuals are involved in the design and application of, ultimately generates the types of results in these dynamic systems that we're talking about. Right. So this is where we basically take away that artificial sort of premise that you have researchers and you have practitioners, and really you bring the two together and say they are one and the same. So with that, I said at the beginning, I would put this back up. There's a QR code that you can scan and go get a PDF of these slides. So you're welcome to do so. You can always email me. And of course, if you want to learn more about what we're doing here at Washington University, I gave you a few examples. You can go take a look at our website, which is at the bottom of the page. And with that, I'm happy to answer a few questions if you have them.
Philip, thank you. This was an outstanding talk. I think this talk is truly a gateway for this new seminar series. We really appreciate you being here. We've got about 4 minutes till the top of the hour. Any questions from folks? Feel free to speak out.
Hello. Hi, can you hear me?
Yes.
Yes.
This is Ronnie Rao. I'm Medical Director of Primary Care. So I come from a primary care angle, and it's very obvious that we can learn a lot from our colleagues in computer science, and it's an exciting time. My question has to do with predictive decision making. You know, if the prediction is wrong and a decision is made, how do you attribute liability? You know, when you're using a spectrum of AI application, like from assistive function to a fully autonomous functions, and then, you know, sometimes those fully autonomous functions are not visible to us. You know, when a mistake is made, when an error is made, you know, where does the liability lie? You know, with the end user or with the developer, and also to what extent do we get informed consent from patients? How do we explain this to patients when we get informed consent?
Yeah, so both excellent questions. So I'll start by saying I am a firm believer right now that most of the interventions in sort of this predictive analytics space can and should be interventions that are more sort of what we label in sort of the decision and implementation science domain as nudges. So not taking the clinician out of sort of the loop, but rather sort of providing a nudge towards, you know, additional steps that may not have otherwise been taken. So to your question, let's say we have a project right now where we have a mortality risk prediction tool that's used in the emergency department that looks at patients who have longstanding chronic or acute disease conditions and a high mortality risk that are on a trajectory where they may be admitted to the ICU from the ED. And all we do is actually make a suggestion in the EHR that they get a palliative care consult before they send that patient to the unit. And in reality, we haven't really changed anything in terms of the decision-making process because the provider has the choice to take that nudge or not. But we have changed outcomes, and actually we've seen very positive changes in terms of end-of-life experience for many of these patients as a function of providing that nudge. So I would argue with the current state of the art, we're not ready to create closed loop or sort of black box systems, even though I know there are some that are arguing for that. I think right now we're really talking more about supportive systems that do not take humans out of the loop. Now, I will say I'm not an attorney, but we do have an institute here called the Cordell Institute that studies these issues, and it's a joint institute with our law school. And we have been studying through that institute a lot of these really critical questions around sort of liability and attribution. And I will be really truthful with you. I think they remain very unclear at present, which is why I also would argue again that we're not ready for truly closed loop systems. As for patient consent, I can just tell you in the case of our current pilot of ambient AI for note generation in our primary care clinics, we are providing every one of those patients with an informed consent up front. We're telling them that we're using this technology, that it will record their encounter, that it will produce a note, that they and their provider will be able to see that note, and that we will then sort of basically anonymize and then ultimately destroy that recording in short order. And if the patients decide they don't want it, then we don't do it. But we are taking what I would describe as sort of an extreme transparency approach with our patients. I will tell you about a week in, so far, our patients by and large have been extremely supportive of this. I mean, still sort of days, but the general response is, as long as I get more time with my doctor and you're going to protect my privacy, I'm okay with this. And we deliver that actually through our patient portal prior to the encounter. We also have it available on kiosks and tablets in the waiting room, and we have paper copies as well. So like we're using every modality we can to make sure that the patients have an opportunity to ask any questions they have. So hopefully that answers your questions, but I would say with consent, it needs to be very transparent. I think in the inpatient setting, it's a little bit harder when we use some of these analytical AI tools like those used for mortality risk prediction. And there, I think one of the things that we have been doing is making very clear to those patients when they're having the conversation, and we've given sort of a script to the patients, to the providers. I go back to that palliative care consult nudge, where the provider basically says, the computer has suggested that you might want to talk to a palliative provider. Do you want to do that? So we're very transparent with our patients, like this is where the recommendation came from.
Yeah, so just to add a layer of complexity to the informed consent question, I'm at the participants in, Fluency Align and taking consent from my patients for AI. But, as you envision many AI tools integrated into the record, so maybe predictive decisions for whether a patient would get sicker, limited, lifespan limited. So that plus, the dictation system plus something else, or renal dosing of medications. When you have multiple assistance, multiple avenues of assistance from AI, do you take one general, consent?
Yeah,
Is that
it's an interesting question. I mean, I will share with you in the NAM group that I mentioned earlier, one of the things that has sort of surfaced in that conversation is the idea of, much like we give other details in after visit summary, that we would provide basically what would be a report card after the summary that would say, these are the algorithms that were used during your encounter and what they predicted or otherwise output to make that transparent. That's less about informed consent and more about sort of informing how the algorithms have been used. Although I would also point out, we use algorithms every day in medicine today that are not AI driven, that are intrinsically biased based on incomplete data. And we don't currently consent our patients when we, for example, calculate a GFR, even though the GFR is actually quite flawed. So I do think there's sort of a real complexity to what you're asking, right? Because it's not as though there's a new problem, they're just a new class of algorithm.
Thank you very much. It was a great talk.
Could I ask you a question about the nudge that you're talking about for
Sure, yeah.
the student, the clinicians in the clinic? If the clinicians are so rushed and they have to see these patients within a certain time frame, a lot of them are not burnt out. They just have to get there and see the
Right.
next patient. Is there a way that the computer would nudge them that they're forgetting to ask certain questions? Would the computer be, would AI be sophisticated enough at some point to be the mentor of that physician that you might want to ask this question, and they're catching on to what the disease is, but this person is rushing through it and not putting it down, and it's not there?
Yeah, so many of you are probably familiar with this concept of clinical documentation improvement, CDI, which is sort of a practice that's been implemented in a large number of health systems to sort of look at the quality and completeness of documentation and provide feedback to providers on maybe areas that they are frequently missing. And it's largely done retrospectively right now. And unfortunately, it's frankly largely done by people in revenue cycle because they're looking for documentation that can be used to better code the encounters. I think there is a belief, and we have seen technologies and had some demonstrate to us, that you could turn clinical documentation improvement into a real-time exercise, whereby the AI would basically track the encounter and then anticipate where there may be gaps in the documentation, and to your point, nudge the provider to say, don't you want to document X during this encounter? That is something that's on the roadmap for most of the major electronic health record vendors and the major AI vendors, because obviously retrospective clinical documentation quality improvement is not very helpful other than perhaps for training purposes, whereas real-time documentation quality improvement would address some of the issues that you raised. But I would tell you from what I've seen so far, it's still very early days. I've not seen a system that I would describe as being sort of, ready for prime time.
If you had an EHR system that actually captured that with AI, you would have a very accurate EHR system.
Well, I think that's aspirationally where we want to get to. There's no doubt about it. I think the idea is that ultimately, especially generative AI, should give us the ability to sort of make the electronic health record much more of a assistive technology to the provider rather than something that is a detractor from the clinical encounter. But there's still a lot of work to do.
Mm-hmm. Thank you. This was great. Wonderful.
Terrific. We've gone over 3 o'clock here in the Eastern time zone. Again, Dr. Payne, thank you for helping to launch our CTSC Artificial Intelligence Seminar Series. We're super grateful. Outstanding talk, and we're looking forward to working together, hopefully, again in the near future. Thank you.
Great. Thank you.
Thank you. Great talk.